In this video, we're going to talk about sets and set notation. A set is a collection of objects. Typically in algebra, they're going to consist of numbers or variables, but in the real world, sets can include any objects at all, days of the week or months of the year, or objects that belong in a kitchen, anything of that nature. Now, braces are used to indicate a set. So whenever we have a set of objects, we're going to open it with a brace and close it with a brace and list all of the members or elements of the set one by one, and we're going to separate them with commas. This first set is a set of 4 numbers, 1, 2, 3, 4. The set is opened with a brace and closed with a brace, and each of the numbers is separated with a comma. Likewise, in the second example, we have January, June, and July. This is a set of all the months that begin with the letter J. Again, braces are used to indicate the set, and commas are used to separate each set member. Let's do an example and build our own set. Write the set containing the last 5 letters of the English alphabet. Well, to do this, we need to know what the last 5 letters of the alphabet are. In this case, it's V, W, X, Y, Z. So we're going to place them in order. We're going to separate them with a comma and place them inside braces, just like this. This would be the set that identifies the last 5 letters of the English alphabet. The first few types of sets that we looked at were called finite sets, and because they had a countable or a finite number of elements in the set. Our first set had 4 members, our second set had 3 members, and our third set had 5 members. These are finite sets because you can actually count the number of elements or members that the set has. Another type of set is an infinite set because it has an infinite number of members in the set. One example is going to be the set of natural numbers. Now, the set of natural numbers is going to be denoted by the capital letter N. And these are the numbers that we use to play hide and go seek. So you count starting 1, 2, 3, 4, 5, and so on. You'll notice that the set is written again in set notation with the open brace and close brace. The members are listed with commas separating them. And the ... is called an ellipsis, and that just means and so on. The next infinite set that we're going to deal with is called whole numbers, which is denoted by a capital W. This set is essentially the same as the natural numbers or the counting numbers, except it includes a 0. So in this case, we have our set, open brace and close brace, 0, 1, 2, 3, 4, and so on. Again, all the members are separated by a comma. Our final infinite set that we're going to deal with is the set of integers, denoted with the capital letter Z. In this case, our set continues infinitely to the left and infinitely to the right, because it's going to include the negative numbers and the positive numbers. We have -2, -1, 0, 1, 2, and so on in both directions. So it's basically going to be the whole numbers and their opposites. The third type of set is the empty set. And we write the empty set using empty braces or the null set symbol. Well, think about what the empty braces means. If this is set notation, we have an open brace and a closed brace, and all of the members are in between the braces, separated by commas. But with the empty set, we don't have any members. It's going to be blank, which means it's empty set, no members. The null symbol also represents an empty set. I will say that some people get confused by the two and try to combine them, and they'll try to write something like this. But why is this not okay? Well, this is not an empty set, because using set notation we have an open brace and a closed brace, meaning we have a set. But inside this set, we have a member, don't we? In fact, its member is another empty set. So what we have here is a set that contains an empty set. So this symbol would not be acceptable when representing an empty set. So far, we have written sets in roster form, or roster notation, which means that we have basically listed each element or member. In the case of infinite sets, we have listed the pattern of the set. We can also write sets in what we call set builder notation, where we describe what the set contains. In these two examples, we're going to describe the whole numbers from 0 up to 3. In roster form, you'll notice we've just listed them, 0, 1, 2, 3. However, in set builder notation, we're going to do something a little bit different. We still have the open brace and the closed brace, but we're going to read this and we're going to say the set of all x's such that x is a whole number less than 4. In this case, this is describing what the set is. We're saying our variable is x, and x can take any value as long as x is a whole number less than 4. And we know from looking at the set of whole numbers previously that whole numbers are 0, 1, 2, 3, 4, and so on. But whole numbers begin at 0 and do not include negative numbers. So when we say a whole number less than 4, we're starting at 0 and we're ending at 3 because 3 is the last number that is less than 4. I'll do a couple more examples of these later to give you a better idea. Let's take a look at a couple of other symbols used in set notation. This first symbol is called the element symbol, and it's kind of shaped like a funny E. And when we read it, we read, is an element of. And I've put this in set builder notation so you have the opportunity to see another example. So -3 is an element of the set, hence it has the braces, of all x's such that x is an integer. And recall that integers are the whole numbers and their negatives. So -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on in both directions. Likewise, we have its counterpart, which is not an element of. So similar to equals and then putting a slash through an equal sign and saying not equal to, we have is an element of and is not an element of. So we've taken our funny little e and just put a line through it saying not. So this next statement will read, -3 is not an element of the set of all x's such that x is a whole number. Recall that whole numbers begin at 0 and work their way up. 0, 1, 2, 3, 4, and so on. There are no negative numbers included in the whole numbers. Thus, our -3 is not an element of the whole numbers. To finish our lesson on sets, let's take a quick look at subsets. I have listed here 4 sets, set A, B, C, and D. Set A contains the first 8 natural numbers. Set B are the first 4 even numbers. Set C includes the first 5 odd numbers. And set D has a lone member, just 5. So when we deal with subsets, we can say that set B is a subset of set A because every member that's in B also appears in A. Likewise, we could say that set D is a subset of set A because its lone member 5 also shows up in A. However, let's take a look at set C. Is set C a subset of set A? Well, the question you have to ask yourself is, are all the members that are in set C also in set A? Set C contains 1, 3, 5, 7, 9. Set A, 1 is there, 3 is there, 5 is, 7 is, oh, but not 9. So since not every single member from C is also in A, set C is not a subset of set A. So let's look at how we write these. we're going to have another symbol, and it's going to be our subset symbol, as shown in these examples. And similar, we have a is not a subset, where we just take our subset symbol and put a slash through it, saying not. So in the first example, we're saying that set B is a subset of set A. All of its members are there. The second one says set C is a subset of set A, which in this case is not true, because we have a 9 in set C, where set A does not have the 9. So to change it, we're just going to put the slash through it. Just like that. And now it's C is not a subset of set A. Next we have D is a subset of C, and it is because D's lone member 5 does show up in C. But C is not a subset of B, because none of the members of C are found in set B. This concludes our discussion on sets.